Good morning or good afternoon, depending on where you are. My name is Professor Orata. We are continuing with our lectures in thermodynamics. Today we want to look at the steam turbine. The steam turbine is a very important tool in the sense that it is in the steam turbine where the high thermal energy of steam and the high pressure or pressurized steam is converted into mechanical power. And that mechanical power can be used to do several things, because that mechanical power results in some rotary motion, which is very important in terms of the interconnection of the shaft and the generator to generate things like electricity. So it's very, very important. Steam turbine is very important. It's important in industrial setups. It's important in power generation and so forth. So we want to look at the steam turbine today. And we need to remind ourselves, there are other lectures we have now talked about the Rankine cycle, the interface Rankine cycle. We have talked about steam generation. So it's good, I advise you to look at them. It's good for continuity purposes. Let's just remind ourselves very quickly about the Rankine cycle. We had the temperature, entropy matrix, and the Rankine cycle. The Rankine cycle one, two, three, 4, 5, 6. The Rankine cycle. So in the Rankine cycle, we had this kind of a schematic. We have the boiler, is the steam generator. We have the pump. We have our condenser. And then we have our turbine. So this corresponds to the boiler step, this the pump step. So we have the boiler step, we have the pump step, we have the turbine step. And we have the condenser step. So that effectively the steam turbine is really uses the series of expansion, isothermal expansions, adiabatic expansions, effectively. In fact, it's the idealized heat engine, where you remember we said that we have various steps. Like, for example, if you look at the Carnot cycle, we had the isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. It idealizes that system very, very well. That is the steam turbine. And so we look at the steam turbine. At this particular point, we have work outputted. Of course, we have work inputted when it comes to the pump. And if you look at our earlier lectures, we are able to tell what is these quantities in terms of efficiency of this system, which is the work outputted divided by the work outputted over the input. And we have looked at that in our earlier lectures. So just look at the lectures in Rankine cycle, and also I advise you to also look at the lecture on steam generation. Now, when we are talking about the turbine, we are talking about the turbine, we want to concentrate on just some few aspects of it. When we are talking about the turbine, we want to concentrate on some few aspects of it. One, we want to look at the nozzle. We want to look at the rotor and probably discuss something very vital about diaphragm and talk about the casing. Now, the model which I like to talk about more often is the Pelton turbine. The Pelton turbine. So I normally like about talking about the Pelton turbine. And in the Pelton turbine, we have our casing, casing, you have that wheel, you have the spear, it's the wheel, this is the nozzle, so of course there's the Pelton duct, which brings the steam. That's the duct which brings the steam. And then of course we have here the blades. We have the blades. Of course we have our runner. We have the vanes or blades. In most cases, the casings have exterior and interior casing. And so we have this kind of a thing. Now let us look at it on a more serious note. Now, the steam turbine, we have said, converts that thermal energy of a pressurized steam into mechanical power. And that mechanical power will, of course, result in shaft work, which is normally rotation. It rotates, and that's why we're able to link it to the generator to generate electricity or power. Now, let us look at the significance of these quantities. First, the nozzle. When you look at the nozzle here, the nozzle plays a very important role. Think of it this way. You have a nozzle. And in this unit, this nozzle, we have the high pressure steam from the boiler. And of course, its velocity is very low. It's high pressure and velocity is very low. Now, when it goes through the activity of this nozzle, whose cross-sectional area varies, it can be a divergent one or convergent nozzle, we end up with low pressure. But now high velocity. So we have this high velocity steam jet, which actually will impact on the vanes or the blades on our runner there. This is as an example where we are thinking of the drum type turbine. This is the disc type, but we are talking about the drum type. We are going to talk about that. We are going to talk about that when we are talking of these other things. Now, let us just take an example. So, what is happening is that there is enhanced velocity. By the nozzle. And this leads to greater impact by steam on the blades or vane. Now, let us look at it. How does this happen? Now, if we take, for example, that we have this nozzle fluid in, let's call it F1, fluid out. So it can be gas or liquid. Let's just take that example there. Now, if we look at what's going on in this nozzle system, remember that from first law of thermodynamics for steady state flow processes, that is flow processes, dH plus d c squared over 2 plus d dz is equals to dq minus dw. Now there's no work done in the nozzle, zero. And when we are talking about the turbine, that's an isentropic process. From the Closius inequality, dq will be zero, so it's like adiabatic. And then there is no significant change in the datum level, so the potential energy is not changed. So we can think of that as also zero. But we have talked about velocity, low velocity to high velocity. It has changed from low velocity to high velocity. So velocity, we cannot assume that. This deals with kinetic energy. This deals with potential energy. And we have said that is zero. So we are left with dH is plus dc squared over 2 is equals to 0. Remember, c is the velocity. C is the velocity. So what do we have? If we say the inlet, let's mark the inlet as 1, outlet as 2. Then we can say that this integral of dH 1, 2, of course I want to move that this side, minus integral of dc squared 2 from inlet, outlet. What do we have here? What do we have? 1, 2. What do we have there? So what we have here is very simple. We have H2 minus H1 is equals to C squared 2 over 2, and of course inlet, outlet, and that will be C2 squared over 2 minus C1 squared over 2. Now what does that mean? You know that we started with low velocity, now it's high velocity, and it is significantly enhanced that you can assume that it is much greater than, if you can assume that C2 is much greater than C1, so that this we can assume diminishes, so that we have H2 minus H1 is equals to C2 squared over 2. And so what does that tell us about the velocity? A simple rearrangement here tells us that C2 squared is equals to H2 minus H1C, or we can simply say C2 is the square root of this is 2, is the square root of 2 into H2 minus H1. I repeat, the nozzle achieves a very important thing. One, it enhances the velocity of the steam. Of course, that increases the impact on the blades which are mounted on the drum. So we are coming to that portion now, the rotor. What is the rotor? Let's just have a sketch. Let's just sketch it. We have a drum. I'm thinking of the drum type. There are two types of the rotor. There's the drum type and there's the disc type. And these are akin to, for example, if you look at the braking system of a motor vehicle, we have the disc type and we have the drum type. So mechanically, they're just things which are moving, they are complementary in their discussions. Now, we have the drum type. And in this drum type, we have a shaft. And on this drum, it's just a sketch. Let's try to sketch it as best as we can. But you can see it's cylindrical. I hope it shows clearly that it is cylindrical. Now, on this drum, so we have the shaft here, and we have the blades. We have the blades. Let's call this the vanes or blades. And so what happens? The shaft, and this is the wheel. The shaft plus the wheel constitute the rotor. Now, of course, you see the word rotor comes, you are thinking of rotation. Now, this shaft is mounted onto a bearing. This shaft is mounted onto a bearing. Mounted onto a bearing. The shaft is mounted onto a bearing. Mounted onto a bearing. So a bearing facilitates rotation, movement. facilitates rotation, easy movement. And most of the places, most of those components, mechanical components, where there's movement, there will always be a bearing. Can be a ball bearing or a roller type, the ball type or the roller type. But it facilitates that motion. So that shaft is on a bearing so that it can move. You can imagine if it wasn't the frictional forces and the consequent energy dynamics related to that movement. You can imagine what would happen if you're trying to move that shaft on another metal itself. You know what will happen? First of all, because of frictional forces and it will lead to asymmetry in terms of even that hole. It will literally eat up the hole, and the next time they will be wobbling. The wheel will be wobbling and wobbling and wobbling, and of course, they're all consequences which come with that. Mechanical consequences which come with that. So it's mounted on a bearing for ease of motion. And we have the vents here. So that steam at high velocity impacts on these vanes. High velocity impacts on these vanes. And of course it percolates through, and that has effect on it. But the pressure is not changed significantly. The velocity of the steam will change, the pressure will not change significantly. And so that's very, very important. And of course, when it is moving, remember now, when it is moving, rotating, it's connected to a generator. And of course, in that system there to produce electricity, we have several things. There are magnetic fields involved and so forth. As it rotates, there are many things which are changing in that particular system, and it's in a magnetic field. It's a magnetic field, so electricity is produced. That's the rotor. Very important. That's very, very important. We have the drum type is what we have talked about. There is the disc type, which we don't want to spend our time on. We have the disc type. That's like I told you, we have drum type for brakes and we have disc type for brakes in motor vehicles. And the principles are basically the same. So these are also discs which are mounted, and in between these discs there's a diaphragm and they are mounted, and in between these discs fluid is able to flow. And so this does not matter much. The net result is the same. Only in terms of the efficiencies and so forth. If you look, for example, in terms of the surface areas involved and any other of those structures, those are things which will affect the operation one or the other, but they're all very effective. But I've chosen to work with the drum type, which is a lot much more clearer than trying to draw the picture of discs in the system. And then the other thing which we need to look at is, in passing, is the casing. We have already seen in the Pelton turbine, which we have talked about the casing. So the casing, about exterior, it's normally two-layer exterior, and you have the interior casing. And of course the rotor, which you now know is the wheel together with the shaft, are enclosed in that particular casing. It's enclosed in that particular casing. And so finally, you have the diaphragm. The diaphragm, think of diaphragm just like we have diaphragm even in the human system. But in this particular case, this diaphragm links it to the wheel, links the wheels, and it affects the distribution of the steam one way or the other. So it doesn't play a very critical role, but it affects the distribution of steam. distribution of steam in one way or the other. And of course, that will impact on the veins and everything, and so forth and so forth. Now, that's in passing. You want to make sure that when you're dealing with your steam turbine, you want to make sure you have reduced significantly frictional forces. That's where the bearings come in. And you want to make sure there are no leakages of steam. You don't want to have leakage of steam because you know what will happen. Like just when we talked about the piston cylinder model in pressure volume work, we said that the piston must be perfectly fitting so that the gas does not escape by the side between the piston and the cylinder. So you need it to be kind of completely airtight so that you don't there's no escape of steam from your system. And in terms, and even when you're using it in power generation, for example, you want to make sure that the electrical resistances associated with your power electric generation unit are controlled, because remember, resistance plays a lot of electrical resistance is basically like just like loss of energy when you're doing, like for example, when you have mechanical work. If there's excessive friction, of course, energy will be lost in form of heat and so forth. So electrical resistance is basically also doing the same thing in the electrical system, leads to losses from your electrical system. And so basically the turbine remains a prime mover in most of the industries, in power production and so forth. So all the turbines, irrespective of when they were designed, the old and the new, they work based on the same principle. We have the rotor, we have the wheel, we have the blades. So the steam, the high pressure steam, which has a lot of thermal energy, this thermal energy is converted, is harnessed by the turbine into mechanical power. And the mechanical power, of course, when you have it now finally ends into kinetic energy, because everything rotates there. So you have the rotating shaft. That rotating shaft is interfaced with your generation unit for electricity or power, or whichever purpose you have put it for, and all this is interfaced. So basically they're the same. There has to be casing, which is not only protective, but facilitates all these things in the sense of containment of those activities involving fluids in that particular system. And we have talked of the various types which you can use. You can use the modern types like the disc type, which is now common, but then the drum type is very, very common. It's also commonly used because it's also very efficient, very, very efficient. So basically, those are just the highlights of the turbine. And the nozzle, very important unit there, because it's the one which enhances the velocity of the steam. And you have seen what happens in terms of the enthalpy change. And remember, enthalpy is energy. It's energy content. It's energy content. Enthalpy, when we talk of the change in enthalpy and a constant pressure and so forth, or under constant pressure, that is enthalpy is heat transfer at constant pressure. So it is very, very important. That is related to the velocity, as we have seen in that particular equation. So the the nozzle, the steam is at high pressure, moves in, low velocity. When it goes through, there's a symmetric thing in terms of cross-sectional area. When it comes out, is low pressure but high velocity. So I think we'll stop at that particular point. For now, we'll continue with our lecture series.